Filtering is another circuit of the signal conditioning, where in the filter, or by using filter, we are going to allow certain frequencies to pass through and other frequency to be rejected. That's simply what the filter is. So certain frequencies or certain signals will be allowed to pass through, other signal will not be allowed to pass through this. So now the filter are having two classes mainly. They are passive, which made of capacitor, resistor, and inductor, and active, which we use the amplifier discussed just now, but with different circuit arrangement, we can make it as a filter. We will start the theory of filter. Mainly here we are going to discuss the low pass filter. So let us think of filter types so that we can understand the low pass filter. Filters, in terms of characteristics, there are four types: low pass, high pass, band pass, and band reject. What is the meaning of each of them? Low pass means low frequency will pass, high frequency will be rejected. High pass means the opposite. High frequency will pass, the low frequency will be rejected. Band pass means we are going to select certain range of a frequency to pass. Certain range of a frequency to pass. That's why we call it band pass. Band means certain range of a frequency. That band will pass and the other will be rejected. And band stop will be the opposite. Means certain band will be stopped, will not be allowed, and the rest will be certain band will be stopped or rejected, and the rest will be allowed. If I look at the characteristics of low pass filter, let's start with low pass filter as I discussed just now. Low pass filter means the low frequency will pass. So we are showing the characteristics, or what we call ideal characteristics, on this relation, where this relation is showing me, or this characteristics is showing me a relation between frequency and magnitude. Low pass means when the frequency is low, it will pass. At certain point, we call it cutoff point. Cutoff point, FC is the cutoff frequency. At the cutoff frequency, the frequency are not going to be allowed. What do I mean here? Let us say the cutoff frequency is 5 kilohertz. So there is a range of frequency entering. Let's say 1, 2, 3, 4, 6, 10, 100. They are kilohertz, all of them kilohertz. Okay, I hope you catch what I mean. All kilohertz. When these signals are entering to the circuit, you will find that 1, 2, 3, 4, 5 will pass through. The rest are rejected. So let us assume that this is the circuit. If I assume that this is the circuit, here is the signal or the input signal, and here is the output. When I enter a signal, let's say the cutoff frequency, as I said, 5 kilohertz. Let's say the signals enters is a mixture of 1K, of course, all in hertz, 1K, 3K, 4K, 10K, 50K, all in hertz. If all these signals enter to the circuit, you will find on the output only 1K, 3K, and 4K. The rest will not be allowed. So 1, 3, and 4 will be, if I assume that this point is 5, according to what I said, 5 is the cutoff. So 1 will pass, 3 will pass, 4 will pass, but the others here will be rejected, will not pass. High pass, now the idea is clear, so I'm not going to go to the detail. High pass means the low frequency will be rejected and high frequency will be allowed to pass. Low frequency up to the cutoff point will be rejected, will not be allowed to pass, and the others will be allowed. Band pass means we have two cutoff points, or 2 points where the frequency is going to be rejected, F1 and F2. So the band is the frequencies between F1 and F2. Below F1, all rejected. More than F1, F2 or F high, we call it F1, F high, or F low, F high. So higher than F high, it will be rejected. the only signals will pass through is in the range within F1 to FH. Opposite is band stop or band reject. Sometimes we call it band stop or band reject. So certain band between F1 and FH will be rejected, not allowed to enter. And the rest will pass through. So this will pass, this will pass, and here it's going to be rejected. Low pass filter is important in instrumentation because there are many high frequency signal mixed with our main signal. We don't want that high frequency. We will clear them out and we will keep the signal which we want, our own signal. So low pass filter, as we mentioned earlier, it will reject the high frequency signal. Here we are going to study how it's going to reject, how it's going to prevent certain range of frequency and will allow certain range. We are going to make a passive, or we will study passive filter, which a combination of resistor and capacitor in series. We are going to assume input voltage Vn and output voltage Vout. We want to see how the output voltage will be only the frequency which we want them to pass. So the low pass filter, which we are going to study here, it's going to be a combination of resistor, as I mentioned in the previous slide, and capacitor connected in series, where the input is applied between these terminals and the output is going to be taken from the terminal of the capacitor. Now this kind of filter, we call it a first order filter because it has only one reactive component, which is the capacitor. One reactive component make us call it first order kind of filter. Let us analyze it in the next slide, but before I go to the next slide, I want you to know that all the signals a mixture of the signal we want and we don't want will enter here, and here we are going to get only the signal which we want, we accept. So in terms of analysis, we are going to consider the electrical circuit analysis, the AC circuit analysis. We know that if I want to calculate the reactance of capacitor, it's equal 1 over omega C, 1 over omega C. Okay, so the reactance of the capacitor is 1 over 2 by Fc, where this is omega, as you know. Okay, in ohms, that's good. And if I want to get the impedance is equal to under root square of R square plus XC square. Now, how am I going to calculate the output voltage? The output voltage is simply calculated by voltage divider rule. So voltage divider rule is saying that this reactance divided by the total reactance is here, or the impedance, multiplied into the input voltage is equal to the output voltage. That's what he's shown. V out is equal to Vn multiplied into reactance, where the voltage is taken from, divided by the total reactances, which the impedance. Or here we are putting it in a simple format. So as I mentioned earlier, the cutoff frequency is the point where the filter considered as rejecting some frequencies. What do I mean here? If you look at the characteristics, the characteristics are shown here. So there is, for low pass filter, there is a pass band starting from very low frequency, and it's going to continue until certain point. At that point, we call it the cutoff frequency. Anything below this frequency will pass. Here he call it pass band. Higher than this frequency is going to be rejected, and you notice that the magnitude is dropping. Now, where to select this cutoff frequency at what point? It's at certain point, not at the knee, here. We are not selecting it here. We allow the voltage to drop to certain level. We call it 3 dB. When we reach to this one, any frequency after that is considered rejected. So again, I'm not going to take the voltage on the output to be maximum. If the voltage drop little bit is no problem. So that little bit is given here as a minus 3 dB. Regardless of the detail of this dB, but it's just I want you to know that we will allow certain frequency of the output magnitude to drop, and then we will take the cutoff frequency, which is going to be this point. We are not going to take it at this point, no. We are taking it, we allow some drop. So that's the characteristics of low pass filter. So again, we are going to check after a while, how are we going to reject by question? We will get the question, we will calculate a certain low pass filter circuit and see how the frequency is to be rejected or to be allowed. Rejected means stop or allowed. Before I go to the example, I just want you to know that the cutoff frequency can be calculated as seen here in the RC circuit, in the RC low pass filter. So we can calculate this point, the cutoff frequency here, this one, can be calculated using this formula. So the formula is 1 over 2 pi RC. So the value of RC are going to decide on at what frequency we will, or at what value the cutoff will start. Okay, hopefully this example will make us clear about the process of filtering. Let us read the question together. The question is saying low pass filter consisting of 4K7. 4K7 means 4.7 kilo ohm. 4.7 kilo ohm. Okay, 4.7 means 4K7 means 4.7 kilo ohm. I hope you remember this from the electrical circuit analysis. 4.7 kilo ohm. So this resistor is 4.7 kilo ohm. Fine. In series with a capacitor of 47 nanofarad. This one is 47 nanofarad. Connected across 10 volt sinusoidal supply. So the voltage here, or the power supply is 10 volt sinusoidal supply. Calculate the output voltage. We need to know what is this output voltage at frequency of 100 Hz, then 10,000 Hz. So if the frequency here, F equal to 100 Hz, what will be the output? And after a while, we are going to check if the frequency is 10,000 Hz, what will be the output? So let us see how to deal with this matter. Of course, frequency will affect what? As at the beginning, we are going to deal with the circuit at frequency of 100 Hz. So we are going to calculate the output voltage. We are having resistor in series with capacitor. If I want to calculate the voltage of the capacitor, we are going to use voltage divider rule. But capacitor cannot be used in farad. We have to express it in ohm. That's why I need to convert it to ohm. So to convert it to ohm, we are going to calculate XC. XC equal to 1 over omega C. This is omega, or 1 over 2 pi F C. When you substitute the quantities, 2 into pi into F equal to 100. This is our point. Our point will come here. F is equal to 100 into 47 into 10 to the power minus 9, because nanofarad. It will give me this very big resistance. It's very high resistance. So the resistance here, it's very high. Consider something like open circuit. I mean, it's very big resistance. So you will find the resistance is equal to 33.8 kilo ohm, around 33.8 kilo ohm. Okay, considering this resistance at this point, calculate the output voltage. Output voltage is equal to, by voltage divider rule, it's equal to this reactance over the total reactance into the input voltage. So the output here is equal to the input voltage into the output reactance over the total reactance, which will be equal to 10 multiplied into these values, which equal to 9.9. Now, I hope it's very clear that 10 at the input, 10 volt, will result in 9.9 volt at the output. So this filter, we sent 10, we got 9.9. So we assume that the signal pass. no problem, nothing happened to the signal. If I get this voltage very low, then we assume the signal is not passing, but actually it's pass. 10 volt applied, around 10 coming to the output. To catch it, to feel it, let us go to the other option, or the other part of the question. In the other part of the question, he said, what if the frequency of the source is the same thing, everything is the same, but the frequency of the source is 10,000. If the frequency is 10,000 as seen here, how the things are going to be. So we will go follow the same style. We will calculate XC, but this time XC is very small. XC is very small. So it's something like taking all of the current. It will not allow current to go out. Or I can say no voltage will drop on it. But I don't want to think of it this way. I will calculate it regardless of the what's happening in behind. So XC is equal to 338.6 ohm. With this value, let us calculate the output voltage following the same style as before. So we found that the output is 0.7. So I am sending 10 volt from here. I am getting at the output 0.78. That means the signal is rejected. It's not passing through. Signal is not passing, which means now I can say 100 Hz can pass, 10,000 cannot pass. 100 Hz can pass, 10,000 cannot pass. So that's how we are filtering out some high frequencies. That's how we remove high frequency signal from our main signal. Keep in your mind here, I didn't show the cutoff point, but we can calculate it. Once we have R and C, we can calculate the cutoff point to know what are the frequencies which will be allowed and what are the frequencies which to be rejected. In this example, it's very simple. It's a low-pass filter with the resistance of 240 and the capacitance of 0.22 microfarad connected across 10 volt sinusoidal supply. Calculate the cutoff frequency. So I don't need the supply because he wants only the cutoff frequency. For the cutoff frequency, I need to know the value of the resistor and the value of the capacitor. So the value of the resistor 240, the value of the capacitor is 0.22 micro, or 0.22 into 10 to the power minus 6. When we substitute both the quantities, this is C and this is R, substitute them, you are going to find that the cutoff frequency is around 3 kilohertz. Cutoff frequency is around 3 kilohertz, which means below 3 kilohertz allowed to pass. Below 3 kilohertz, signal will pass. More than 3 kilohertz, signal will not pass. That's all about filtering, and that's all about amplifier and filter. I hope everything's clear. I wish you all the best. Thank you.